everybody. Today we're going to do a lesson on geometric sequences and series. Now the good thing is, even though you've had a little bit of a break, this lesson is going to follow the same exact type of pattern as our last lesson, 8.2, which was arithmetic sequences and series. The only difference is that we know a sequence is a list of numbers that have a pattern, right? Arithmetic, the pattern was plus something or minus something. A geometric sequence, and we had a D, remember, in arithmetic, that was the plus or minus pattern. Here, we have a multiply pattern. So instead of plus D, etc., now we have what's called a common ratio, which is called R. So we have a term times R, etc. So just like we did with the arithmetic, we're going to look to see, is this sequence geometric? Meaning, is there a common multiply pattern to get from one term to the next? So let's check this out. Well, we know 6 times 2 is 12. That's good. But are we going to have times 2 to get from 12 to 20? No, right? This is not geometric. Right? Because in order for it to be geometric, we have to have the same multiply pattern. Right? Now, some of you might have looked ahead and said, but wait a minute, Ms. Brinley, this is a divide pattern. But remember, division is basically, we can think of division as multiplication as well. So while we could think of this as divided by 4, we can also think of it as times 1/4. Okay, so are we going to get from 64 to 16 times 1/4? And look, guys, that's also times 1/4. And that's also times 1/4. And that's also times 1/4. So this is geometric. And my R value is 1/4 here. So from now forward, we're just going to assume we're only dealing with geometric sequences. So we're not going to have to diagnose them as geometric or not. So just like we did with arithmetic sequences, we have a formula that we can use to find the nth term in a geometric sequence. All right, so by nth term, we mean, let's say we want to find, I don't know, the 100th term, right? That means n would equal 100. So if n is really big, we don't want to have to keep plugging in times r, right? It would be nice to have a formula. So let's just do a little anatomy thing here. an is the nth term in the sequence. Right, so like we just said, 100th term, that would be A100. A1 is the first term. And R is the common ratio, or we might want to think of it as the multiply pattern. Right? And N stands for the term number. Right? So for the 100th term, N would equal 100. Okay, so these are the parts that we need in order to write the nth, this formula A sub n. Right? So we'll have A sub n, and n is going to be our variable that someone can plug in whatever term number they want. So what we need to find, guys, is we need to, in order to write our formula, we need to find A1 and R. So what we're going to do, each example is going to become a little bit harder. It's going to, in the very beginning, it's going to be really obvious to find A1 and R. Like here, right, guys? We can find A1. Well, there's A1 right there. Right? And R is just the multiply pattern. So it looks like, to me, this is times 3. So A1 equals 5, and R equals 3. So when I want to go and write my formula, I'm just going to use this. I'm going to say A sub n equals A1, which is 5, times R to the n minus 1. And there is my formula. So now they want us to use this formula to find A8. So to find A8, I'm just going to plug in n equals 8. So A8 is going to be 5 times 3 to the 8 minus 1. Which we know we're always going to do exponents first. And I can just type this right into my calculator. That ends up being 10,935. That's A8. Okay, let's spice it up a little. Right? Again, A1's pretty easy to spot here. There it is, A1. Now notice this time, guys, my R is actually negative. It goes from 88 to negative 44, and then negative 44 to positive 22. So this is times negative 1/2. So A1 is 88, and R equals negative 1/2. So that means I'm just going to use my formula. I'm going to say A sub n equals 88 times negative 1/2 to the n minus 1. And there's my formula. And if I want to find A8, I'm just going to plug in 8 for n. Right? So that gives me, and here a calculator is going to be very important. We wouldn't want to have to do this in our head. So if I punch that in, I get A8 equals negative 0.6875. That's my 8th term, which makes sense, right? It's getting smaller when I multiply it by negative 1/2. Okay, guys, so here we saw A1 and R is pretty clear what A1 and R were. So let's spice it up one notch. And this time they're going to give us R, but they're not going to give us A1. Instead, they're going to give us A4. So again, we've got to find A1 and R. So R is right here. They told me R is 2. And they've given me A4, but I need to find, so I know R equals 2, I need to find A1. Because my formula, I need A1. So let's see here. Okay, let's think about, oops, sorry. We know that A4 equals 12, right guys? And we also know when n equals 4, we can use the information that n equals 4 and A4 equals 12. So let's set up a little equation here. I'm just going to write the formula again. Okay, so we know A4 is 12. So let's put 12 right here. A1 is what we don't know. We know R is 2. And we know n is 4. So now our only unknown is A1. So now we just need to solve. Now remember, there are no pluses and minuses here. This is all multiplication. So it's tempting I'm going to say I'm going to subtract 8, but it's not, right? It's times. So that means I need to divide by 8. And I can see here that A1 is 3/2. Right? And we know that R is 2. So those are the two things we need. So here's our formula. Our formula is A sub n equals A1, which is 3/2, times R, and I always like to put parentheses here. You don't need it, but it reminds you that you'd always do the exponents first. So there's our formula. Now they want us to sketch a graph. So if you guys remember with the arithmetic, when we graphed arithmetic sequences, we saw that there was a line, a pattern, the dots were in a pattern of a line. But this time, our variable is in the exponent. So think back to logs, right? When we graph logs and exponents, do you guys remember the shape of an exponential function is more like a swoop? Right, so let's look at our very first term. So we're going to make a little graph, n on the x-axis, a sub n on the y-axis. So we know our first term, so n comma a sub n, our first term is 1 comma 3 halves. So I can graph 1 comma 3 halves right there. Okay, now we know that r is 2, so our second term is 3 halves times 2, which is 3. So I'm going to graph 2 comma 3. Our third term is 3, and then notice I'm going to multiply that times 2. I'm going to get 3 comma 6. I'm hoping you guys can see the swoop. And then we know our last point is 4 comma 12. So I think we can see this swoopy thing. Now we can see the swoop pattern, but we're not going to join them, right? Because it's not, if we join them, we would be saying that all these values in between 1, 2, 3, and 4 for n are also on our graph, but this is not the case, right? We're just looking at discrete points here. Right? When the first term we have 3 halves, the second term we have 3, third term is 6, fourth term is 12. So we can see our nice swoop pattern. Okay guys, spiced up the most here. This time we're not even going to be given R or A1. Okay, so we have to find R and A1 here. Well, that's always our goal when we're doing sequences. Find R and A1. Okay, so let's first focus on R. So they didn't give us what R is, but let's think about this. We know that if A2 equals 12, so if A2 equals 12 and A5 equals negative 768, well, let's think about this here. That means that we know that A2, how many terms are there between the second term and the fifth term? Well, there are 3 terms between the second and the fifth, right? So let's think about this for a sec. We know that A2 times R times R times R is going to equal A5. So let's think about this for a sec. That means we know that 12 times R times R times R is going to equal negative 768. So R times R times R is not 3R. It's R cubed. Right? So now we're going to solve this. And we get R cubed equals negative 64. And then let's take the cube root of both sides. So now we know R is negative 4. Okay, A1, you may notice, if R is negative 4, all I need to do to find A1 is divide it by negative 4, right? So you can do it that way. Or what we can do is we can say, well, let's do the same thing we did up here. Let's use one of our terms. A2 equals 12. So what I'm going to do is I'm going to put 12 right in here. I'm going to have A1. We know R is now negative 4. Right? And I'm going to make N2. So that's going to give me 12 equals A1 times 4, negative 4 to the first. So we're going to get the same answer as we just would do if we just divided by negative 4. But I wanted to show you guys that even if they give you some really huge A, they don't give you A2, you still can get at it this way. So we've got our 2 pieces, so now we can say A sub n equals negative 3 times negative 4 to the n minus 1. Okay guys, last thing. Sorry, Danford. I have a visitor. He's watching this exciting lesson here. This is our last example. Okay guys, geometric series. We know a series is the sum of the terms in a sequence, right? So we had a formula for this is the sum of n terms. I didn't write this, right? We know S sub n from the last one. The sum of n terms in a sequence. Okay, so this one's different than the arithmetic one. But these things mean the same thing. So A1 is still the first term. R, this time we don't have a D, we have an R, that's the common ratio, or the multiply pattern. And N is the number of terms in the series. Well, in the sequence that we're creating the series. So remember the sigma sign, it looks intimidating, but all it means is find the sum. So what do we need here? We need A1, we need R, and we need N. So A1 is just, I'm just going to plug in K equals 1 to my formula. So let's do that. So I know that A1 is equal to -3 to the 1 minus 1, which is -3 to the 0, which is 1. So I know A1 equals 1. Now the good thing is I can see R just with my very own eyes right in the formula. So in this case, R is equal to -3. And I can also see N with my very own eyes in this sigma here. N is equal to 12. Right? Because this says add up the first 12 terms in this sequence. So we have to be careful here, guys, because remember, exponents always come first. So I have to make sure when I enter this in my calculator, I have A1, which in this case is 1. And then on the top, I have 1 minus, okay, very important, guys, put your R in parentheses because your brain is going to want to make that a plus. And that's not what we do. We have to raise it to the 12th first. So you're going to see that this turns into, it looks like it's going to be a positive number if I do this out of order, but it's actually 1 minus 531,441. And then down here I am going to do the plus. So guys, what this ends up being is S12 ends up being -132,860. Now it makes sense that these are going to be really big numbers because when I start multiplying things by -3, right, they get really big. Okay guys, that is it for 8.3. I will see you guys soon.